Okay, web assign 12B, number 13. The circuit in the figure below is located in a magnetic field whose magnitude varies with time according to the expression B is equal to 1 times 10 to the negative third t, where B is in Teslas and T is in seconds. Assume the resistance per length of the wire is 0.096 ohms per meter. Find the current in the section PQ of length A is equal to 59 centimeters. So you may be wondering at first where to even start with this. But actually, what you have to use here is Kirchhoff's rules from the circuit unit. So what you could do is that imagine, so the EMF, imagine those are like batteries on the circuits. So if you have like a battery here, have that the first EMF, and then you have another battery here, and that'll be your second one. And then your currents would be here, call that I1. This one we'll call I2, and this one would be I3, flowing that way. And you know that from your right-hand rule. So now, if you recall, the Kirchhoff's rules are the loop rule and the junction rule. And we have three circuits here. You have this smaller one here, you have this one here, and then you have the big one. So what I'm going to do when setting up my equations is I'm going to use the two smaller circuits, and then I'm going to use the junction rule just to make things easier on myself. So if you recall from the junction rule, first you have to start with your EMF. So we'll start with the left one first. So your EMF 1, and we'll go this way. So it'll be like here, then go down the bottom, through this side, from Q to P, and then the top. So start with EMF 1, and you need the current and resistance to subtract. So on that left wire there, you have, in the problem, it gives you resistance per length of wire. It's 0.096 ohms per meter. And to get the resistance, you would multiply it by the length of wire. So luckily, it also gives you the length of A in the problem. And that's what the length of wire is in throughout the circuit. So, starting on that left side, your current here would be I2. And your resistance, it'll be, it'll be 0.096 ohms per meter. For now, let's just set up the equation though, so we'll just call that R. And it's along the left side, which is of length A. So that would be first part there. Then you would be going down the bottom. So your current would still be I2. And this time it's along the length 2A. So it'll be 2A RI2, because 2A R being the resistance, I2 being the current. And then along the right side, it's length A again. So it would be AR, and your current here would be I1. And finally, along the top, that's 2A again, and I2. So 2AR, I2. And because this is the loop rule, you will end that with equals 0. Because in the loop rule, basically the voltage going through it, once it reaches the final, once it reaches its starting point, it will be 0. So that was the first one. Now we'll do this smaller circuit to the right, which we can have it going this. So start with EMF 2, and then for your first current, it would be I3, and it's of length A, so RA. And then along the top part, it'll be same thing because current's I3 and the length is A. Then going down the left side from P to Q, it would be I1 instead of I3. So it would be I1RA. And then finally on that bottom part, once again, length A, and it will be back to I3. So I3RA, and that was equal to 0. Now finally, we will use the junction rule to make our third equation to make things easier for ourselves. So as you can see here in the junction into P, I1 and I3 meet at P, and it results in the current I2. So that means that I1 plus I3 is equal to I2. So now you might be wondering, like, okay, that's great. I have 3 equations here, but I have 5 variables. Or well, still like too many variables. Like you have all those different currents. You have, so you have all the currents. And then you don't have to worry about RNA because they're given to you in the problem. You have 0.096 ohms per meter and 59 centimeters. But you also have 2 of the EMFs there. So you might think, how am I going to do that? Well, from Faraday's law, the EMF is equal to the area times dB dt. So you can find the EMF in each part using this formula here. So your first EMF will be equal to A. And if you look back up here, the area here is, the dimensions would be A for the length or width, the width, and then 2A for the length. So it will be 2A times A for the area, and that will be 2A squared. And for your dB dt, you have your B, which is 1 times 10 to the negative third t. So it would be times d dt, and your B was 1 times 10 to the negative third t. And if you take the derivative, you get that the EMF is 2A2, 2A squared times 1 times 10 to the negative third, and that's in volts. Now for your second EMF, if you look here, it is length A and A, so it's square. So it would be A squared times, and then once again, you have your dB dt. It is the same thing that they give you in the problem, 1 times 10 to the negative third volts. So you have your EMFs that you can now plug into the 2 top equations. So plug things in, we have that your epsilon 1, so you have 2, and we'll plug in the A. The A was 59 centimeters, so that's 0.59 meters squared times 1 times, or well, we know it's going to be meters squared, but the total unit here for E1 would be volts, which is what you need. So 0.59 squared times 1 times 10 to the negative third, and this is all in volts, minus I2 you're trying to figure out, but you have your R and your A. So that'd be 0.096 ohms per meter, and then it would be length A, so 0.59 meters. And then that would be times I2. And now you just basically continue on plugging in stuff. So it'd be minus 2, and then your A is 0.59 meters, and then your R is 0.096 ohms per meter. That'd be times I2. Or sorry. Yeah, let's make things simpler for ourselves so that we don't have to write all this out. But basically, these two equations, you can simplify a bit first. I probably should do that first. So that'd be epsilon 1 minus, so if you combine like terms, you get minus 5 ARI2 minus AR1 is equal to 0. Yeah, let's do that to make things easier for ourselves. And then the second one would be second EMF minus 3 AR3 minus ARI1 equals 0. So, and in this top equation, it's RI1. All right, so basically, let's see. So here we could just multiply this by 5. All right. And then to continue on with the minus ARI1, it'll be 0.096 ohms per meter times 0.59 meters, and that'll be times I1 is equal to 0. All right, so now then you also have to do your second equation. So it'll be the second EMF, which is A squared, so then that's 0.59 squared times 1 times 10 to the negative third, that's in volts, and minus, at the simplified equation, it's 3AR3 minus ARI1 equals 0. So it would be 3 times, so your R was 0.096 ohms per meter times 0.59 meters. That was I'm missing variables here. This is RI3. So 3AR and I3, and then minus, so it'd be 0.096 ohms per meter times 0.59 meters times I1 equals 0. Just as a refresher, the ohms per meter times meters would result in ohms, and that's resistance, times your I, which would be current. That's why it would be voltage. So you could subtract your, the EMF, which is in voltages, minus all this, because this is voltage and that's voltage. And same thing down here, voltage, 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 and that's all equal to 0. All right, and then finally you have your third equation, which was the junction rule. You have I1 plus I3 is equal to I2. All right, so now finally you solve for the currents, and what you want here is it's asked for PQ, and your PQ is here, and we label that I1. So if you plug that into your calculator and then you adjust accordingly to units, which is microamps, you will get that I1 is equal to 267 microamps. And that's from P to Q. As you can see up here, 267 microamps. All right. And now what you have to do is direction. So what you have to do here is, as you can see, the magnetic field is pointing into the screen. So that means that the induced current is going to, oh, sorry, first off, the magnetic field is increasing because B is equal to 1 times 10 to the negative third T. So there's no negative, it's going to be increasing. So anyway, yeah. The magnetic field is into the screen, so the induced current is going to want to point out of the screen to basically oppose it. So if you do your right hand rule, which is basically like you're going to have your thumbs up, kind of, and you'll have your thumb pointing in the direction of the induced current. So this will be pointing out of the screen. And if you follow your fingers that are curling in your thumbs up, you will get that the for each mini circuit here, that is going to be curving this way and then curving this way. So what you get is that your induced current on the left one, if you follow it, I'm going to draw it again, it'll go from Q to P. Now on this one though, the right one, it'll be going from P to Q. So they are counteracting each other. However, if you compare the two EMFs, E1 is greater than EMF 1 is greater than EMF 2. Therefore, that means that the force, the EMF on 1 is going to be stronger than EMF 2. So EMF 1 was going from Q to P, it's going to be stronger than the P to Q. So that means that the overall direction is going to be from Q to P. And here, just to draw it out. So if you have your circuits, let's make it this big. So if you have your circuit here like this, you can see which one's the bigger, which one's the smaller. So if it's going like this, and it's going like this, the one going from Q to P is going to be greater than the P to Q one. Therefore, the overall direction is going to be from Q to P. And as you can see up here, it is from Q to P. Now, for reflections, I feel like that this problem was very confusing. I'm not going to lie. Doing this in class I had to really think outside the box, basically. Like, I didn't think I'd have to go back into Kirchhoff's rules. Luckily, I figured that out with them. So, yeah, once we figured out the Kirchhoff's rule, then, yeah, it was just relating everything together with the Faraday's law and all the rules that we have to know. So, yeah, we just had to remember the other things from this unit and then put them all together. And from that, we were able to get our answers.